Welcome everyone to a quick overview video of lesson 1.2 from calculus, which is defining limits. So let's just jump right in. Let's look at this f function here. It's a rational function. We have a numerator, we have a denominator, and I've gone ahead and I've already factored it out for us. Now if we look at this, we have 3 zeros in the numerator and 2 zeros in the denominator, which means that we could look for anything from a very weird cubic graph to what we have here, which is a linear looking graph. And we learned about all of the different ways of figuring out what the graph should look like and so on and so forth during pre-calculus. We also learned that if we had a common zero in the numerator and denominator, it made a whole. So in this case we have two. We have one here at 3 and one here at -1, which I've gone ahead and backed up with this chart here of inputs and outputs. We can see at -1 and 3, it's undefined for both. So essentially what that means is f of -1 doesn't exist. But if we look here, it looks like if we look from the left-hand side and the right-hand side, it looks like it's getting really, really close to 1. And that's what we actually call a limit. So a limit is this idea of we're going to get really, really close to something, infinitesimally close to something from both sides. And in this case, the limit for the f function, as it approaches -1, should be 1. And here's how we write it. We would say the limit of f of x as x approaches -1 would be equal to, in this case, 1. And we can back that up with the graph. It looks like from both ends it's approaching this 1 here. Also from the chart, if we look, the growth here from -1 to 0 is 1, so another 1 would put us at 1. And if we go backwards from the right-hand side, 4 to 3 is -1, 3 to 2 is -1, 2 minus 1 would put us at 1. So we kind of have it backed up from both angles there. Now, does that mean if something's undefined, will the limit always exist? And the answer to that is no. But if both ends do approach the same thing, then it does. And in this case, it does for both 1 and for 3. For 3, it would be approaching 5, right? So let's look at a function where the limit doesn't exist and talk about that for a second. So if I hide these things from us, let's look at the parent function for all rationals, 1 over x. And we can tell from the equation that we shouldn't be able to divide by 0. So an input of 0 should cause us problems. And indeed, if we look at the graph here, it does. But if I look at the left-hand side is approaching -infinity, and the right-hand side is approaching +infinity. And since they're going in two different directions, that limit doesn't exist. But something that's kind of cool is if I raise that x to the power of 2, both ends now, the left and the right, are going towards +infinity, and the limit would exist there, and the limit would be +infinity. And again, I'll show you how to write that real quick. We would say the limit as x approaches 0, and this is g of x, of the function g of x would be equal to infinity. That's it. That is just defining limits, which again is getting infinitesimally close to something, seeing how it approaches from the left, seeing how it approaches from the right, and it has to be approaching the same value. All right. See you in the next video.